I wanted to talk a little bit about dwarf galaxies and what we have learned and what things are still not fully understood in this community. And for that, I thought I would just use this pseudo-review paper that we wrote with Andrew Wetzel and Azif Fatahi last year, just to highlight some of the issues that are, some of them solved, or some of them are still needing an answer. And of this, I thought I would concentrate, if time's allowed, on these four, starting with perhaps the relation between the stellar mass of a galaxy and its dark matter halo, this mapping of how exactly are galaxies populating their halos. So this figure is a compilation from that review paper that shows kind of the state of the art, by 2022 on this problem. And what you see is, if you for a second just look at the panel on the left, you find the halo mass versus the predicted stellar mass for dwarf galaxies that form in cosmological simulations by a variety of teams. It's a compilation of different baryonic models. They all form within lambda CDM. And what you see is that they have more or less converged, except if you take away perhaps the Auriga simulation that we think we understand why it over predicts a little bit the stellar mass at a given stellar halo. All of the other very different, very independent models or treatment of variance will give you an occupation of these dark matter halos that is kind of in agreement. However, when you go to the lowest mass galaxies that I would call ultra faint, defined as lower stellar than 10 to the 5, then the predictions either start to differ or they are kind of scarce. And so that you move on to the right panel over here. Again, these are either the same or a different compilation of very different codes. And you see that in this yellow region, that is this ultra faint regime, there are not many predictions, just because this is hard. These are cosmological simulations that are trying to resolve the smallest galaxies out there. And so for this particular plot, we selected things that were resolved with at least 20 times or 20 particles. And that resulted on this number of galaxies. And you see that if you were to believe something like GEAR, that is a simulation that shows zoom-ins of individual dwarfs, you would be populating a very different mapping between your stars and your halo that if you would run, for example, either Fire or Allison Marvel over here, etc. And it's not only that we don't understand exactly the mapping, but also the exact physics that determines this relation is very much related to the early physics of the universe, and all of these simulations are really not tuned to follow that. They are much better maps of what happens at lower redshifts. So because it is so difficult to resolve these objects, one way to understand or make new predictions is to perhaps forget trying to get the physics of it right and just parameterize this relation in two different ways. And this is something that we did with Isabel Santos last year. That is saying, okay, so we take these simulations and we separate them and we try to describe the behavior. And so we came up with perhaps two different ways of doing this now. Instead of halo mass, what you're seeing here is the velocity, the Vmax of the halo, and again, the stellar mass on the vertical axis. And so you could define this in two different ways. One, you say, well, there is actually an extrapolated power law between these two quantities. Or you could say, well, instead of being an infinite power law here, what we are going to assume is that there is a very strong cutoff in halo mass after which, halos less massive than something will definitely not form a massive or a visible galaxy. And now, because you have parameterized this, parameterized your ignorance in some way, you can extrapolate this to very faint dwarfs. Just by knowing this mapping between the two. This idea is definitely not new. And also Allison and Farah Munshi did something similar, but they were concentrated more on exploring the scatter. This, instead of exploring the scatter, we decided to say, well, what if these two relations were just two different ways of parameterizing it? But it's all the same idea, right? So we don't know really what the mapping is for the low mass dwarfs, so let's check it out. And so what you can do now is to make a prediction for the satellite population of many galaxies. And what you're seeing over here is on the left panel is the prediction of the satellite population for a Milky Way mass object. And in blue is the result of something like a power law relation would be here on the right. And the blue one would be, what do you expect if there is a power law relation all the way down? And the results are very different, okay? So it would be the difference between saying we have discovered most of the ultra-faint dwarfs in the Milky Way. That is shown in the black line. This is the compilation of the known dwarfs in the Milky Way. And you know, if nature is really doing something like a power law, then we would expect, you know, we are missing like a few hundreds, like 7. And this is important, or becomes more important, as we look into future missions or future telescopes like Roman or Vera Rubin, where we will be detecting this very low surface brightness galaxies. And the question is, how do we use them to learn about physics and to learn about cosmology? But for that, you need to understand well your expectations for something as simple as just numbers. How many do we expect to see? So we apply the same for, you know, M31. You get a comparable difference. But what we argue is something very promising, is to look at the satellite population of things like the LMC. And what you see here is a host halo that would have between 50 and 100 kilometers per second. That's the host, so something comparable to the LMC. How many satellites do we expect? And so the lower lines, so this blue and this red, would correspond to a lower V200 for the LMC. And of course, this, the higher blue and the higher red, is for a more massive LMC. And we can compare this with what we know of the LMC, of what we think could be associated to the LMC. You know, Nico has done some work on it. Of course, it's complicated. The LMC is within the gravitational potential of the Milky Way, but you use conservation of angular momentum or conservation of orbits. You can come up with some list of UDGs, some list of ultra-faint dwarfs that could be associated to the LMC. And that's probably what you see over here in black, one of the optimistic counts versus the dashed ones. But you know, you would expect many more, perhaps, if your halo for the LMC is a bit bigger. Now, why exactly the LMC is such an interesting scale is because of the numbers, right? So if you check within 10 megaparsecs of the Milky Way, you will find about 8 galaxies comparable to the Milky Way, which is, you know, nice, but about hundreds of about 100 LMCs. And that means that you can beat down the halo-to-halo variation in a much robust way by observing these hosts instead of going to Milky Ways. And so that's something that the community has started doing already. So this, for example, this is one example, the Delve survey, that has selected LMC-like objects in the field. So they are not processed by the Milky Way. And this would be the predictions. Right, so if you have a relation between M star and M halo that looks like a power law, then you know you would expect about 10 of these ultra-faint dwarfs within the virial radius or projected virial radius of these objects. Whereas if the relation really goes as a power law, it would be a few hundred. And that's something that we will have constraints within 5 to 10 years, and that is actually very exciting. Of course, there are dependencies on all of this. How you moderate scatter, as Allison showed, does matter. For example, the red one, the red prediction, which is just sampling a little bit of halo mass for the LMC in this stellar mass range. If you assume that there is no scatter in this relation, you get a lower amount of satellites. But this is the kind of studies that will really allow you to interpret whatever we observe from to say something whether, you know, cold dark matter or not cold dark matter gives you the right subhalo population. But one would also like to understand a bit better about a bit more about the physics of what is going on. And because of the resolution limitations, one attractive way to look at this is by using semi-analytic models. And what you're seeing here, this is work by Nusha Vasi, who is a grad student at UCR and Carnegie. It's a shared program that we have over there. And so Nusha has been working with Galacticus, which is a semi-analytic model by Andrew Benson. And what she has been doing is to try to understand how the physics in the early universe would impact the number of ultra-faint dwarfs. And her best model comes up with this prediction for an LMC object that is shown here in black with the gray area. So if you attempt to model this a bit more physics consciousness with some physics in mind, it looks like the prediction is closer to something like a cutoff model. So if we point the telescopes to things like LMC in the field, we should find of order 20 to 30 ultrafaints within the video radius of these objects. And of course, that is the prediction, and it would be interesting to see what we see once observations became available. This is a bit of exploration. This is a busy plot, sorry. I will ask you to, for now, look only to the dark red. That is our census of dwarfs in the Milky Way. And in black are different variations of the Galacticus galaxy formation model that shows, for example, how including cooling, molecular cooling in your halos can really help you explain the numbers of ultra-faint dwarfs. So what you get, so our preferred model is this one with the error bars shown over here that matches quite well the number of ultra-faint dwarfs observed in the Milky Way. Now, if you, for example, do not consider H2 cooling and you only consider atomic cooling in your halo, this relation levels up here. So you cannot really form the lowest mass ultrafaints without including molecular cooling, helping your halo form some of the stars. Equally strong is the dependence with the UV background. Okay, so for example, if our preferred background radiation is the updated Fauché-Giguère 2020, but if you were to go to now I will forget the name, Madao, yeah, Hardon-Madao 2012, you see that it's much more depleted in the inner regions. So this is another of the things that become so interesting of this ultra-faint population is because their possibility to teach us about physics in the early universe. But ultimately, we always want to resolve them in hydrodynamical simulations because it might give us a few more clues on spatial distribution or on the structure of these ultrafaints that perhaps semi-analytic models. And this is a figure showing results from the fire simulations. You see these are some of the M11. So these are halos of 10 to the 11 solar masses, virial, so analogs to the LMC, but in the field. And over here, you can see the dark matter component, and over here, the stellar and the gas. This nicely shows how many of these clumps in dark matter never light up. And you actually, only a few of them that are marked here with little stars are the ones that form stars. And so that is the solution to the missing satellite problem. So there is no missing satellite problem anymore. We can solve it by a little bit of understanding of feedback and organization, but other problems remain. So once you get this, you can now go and count how many satellites do you expect for something like the LMC. It's shown over here, satellite mass function for LMC like dwarfs, with some comparison to what we think maybe is associated with the LMC. You see that is shown in black. We already said it's complicated because of the kinematics within the Milky Way, but you can make some assumptions and get with this. And then the predictions are in the bulk. of how many satellites we expect. So that is exciting in a way, but we cannot really go much fainter than 10 to the 4. But yet with these ones, at least we can look at their star formation histories and say something about not only how many of these ultra faints we expect, but also which properties. They should be old, they should be start forming, and things like this. And what we find is that the environment of the LMC themselves might actually cause some quenching to these galaxy companions in a very similar way to how the Milky Way or clusters or groups impact the star formation history of satellites. So to motivate that, let me show you over here. These are simulated LMCs, remember, and then we select all the centrals that we find in those boxes. And as a function of stellar mass, we show here the tau 90. Tau 90 is the time at which they form 90% of their stars, and that's unobservable. So we can use that to quantify whether the galaxy stopped forming stars recently or late, recently or early. And what you see within the simulation is that for low mass dwarfs, these are central dwarfs, low mass dwarfs tend to have a very early quenching time, which is consistent with the idea that reionization depletes them from gas and stop forming stars, whereas more massive dwarfs hang on to their baryons for longer, and then they continue forming happily stars if they are in the field. Now, when you do the same with the satellites that are in those same high resolution zoom-in simulations, what you find is those could be the black symbols and the yellow ones. It's a similar trend.
I'm not sure I understand
yes.
the distinction you're making between satellites and other dwarfs.
Yeah, so these are zoom-in simulations, which means they are concentrating on one object, but they do have a few megaparsecs around. So what we do is we take within this high resolution region things that are resolved, but they are not part of the main halo in the simulation, but they are centrals. They are not really interacting with this main halo, okay? And we call those centrals, and they tend to be a bit lower mass than our M11s. But some of them comparable. And in the second one, these are only satellites. So these are things that correspond to only to the central object in the simulation. Okay, so they are really the satellites of these M11s or the LMC-like objects. Okay, and so the difference here is that these yellow objects over here that don't seem to appear so much here, except for perhaps these two. But so the satellite seems to expand also the intermediate timings for quenching. That is not really in the centrals. What you see in gray is the superposition of the Milky Way data. So just for you to get an idea of where the Milky Way points is, but it's really not too important right now. And so for these intermediate times, then we go back and look at their orbits and star formation rate, and that's what is shown over here. So these are the orbits of these yellow marked satellites. The circle is their infall time, and their triangle are their tau 90s. And so you can see that for all of them, for all of these yellow objects, the triangle is exactly at the time or later than they cross the virial radius. And so we define those as environmentally quenched. And so kind of the take home message from this is that the LMC will have the power to alter the star formation rates of some of their satellites too, in a similar way than the Milky Way did. And of course, that also means that exactly how that quenching happens seems to be through two different or connected, perhaps, processes. One is, because the satellite is star forming and it has these blow-ups of gas, then they loosen up the material, and then nothing gets reaccreted again. And so that quenches this satellite. This is what you can see is different time scale, different time posts for one particular satellite. It was gas rich, it had a blow up event, and then nothing came back to it, so it was quenched. And the other one is these tails that form against the direction of the velocity that typically is associated to just run pressure. All right. So a combination of those two processes seem to explain all of these cases. And of course, it comes with the corollary that the LMC should have an associated CGM, or a prediction for what the CGM of objects like the LMC in the field should have. So what you see here in the maps is colored by either density or temperature, but all of the M11 halos in fire have a substantial amount of CGM or hot corona, or as you like to call it. So this would be also very interesting. Looking forward to observations of CGM around dwarfs, and of course, even for the LMC itself, which seems to require some of this to explain, for example, the Magellanic streams. A bonus is that some of these dwarfs, actually the ones that were quenched, when looked in detail, also displayed tidal streams, which means as we peer deeper into LMC or isolated LMCs in the field, not only we will discover the population of satellites, but also we should find the streams, and actually with a high, larger or a significant number of frequency. All right, so these are, we had in our sample about 8 halos included, and 4 of them displayed these stellar streams in their halos. This is at redshift 0, so they should be observables, and this is sort of a prediction, again, that can be contrasted with observations, very low surface brightness observations coming up soon. Okay, so after that, I'd like to move to another of the tensions that we have heard for, some decades about the core and cusp, inner regions of dark matter halos. Dark matter in CDM is expected to be cuspy. However, if you look at the rotation curves of dwarf galaxies, you see cores. So what's going on? I think by now, the community simulating dwarfs has, I would say, accepted the idea that baryonic physics can actually create these cores. This is something Alison has done a lot of work with, and some other people. This particular is from Alison's groups, but from Fabio, showing that if you check the steepness of your profile in the inner regions, and you do only dark matter only simulations, you get the NFW expected slopes. But now if you put baryons in a way that is realistic or detailed in the small scales, then you get a flattening. So a perfect constant density core here would be a 0. So you see that within this selected mass range, feedback processes can alter the shape of the profile. This is something that, for example, is shown here from fire simulations. The same halo run dark matter only is these dashed lines. If you run it now with baryonic physics, you get this where kind of constant density cores, and the rest seems unchanged. So this is not really something that one team is predicting, but it seems to be a widespread prediction of things that solve or model the feedback sort of on the smallest scales. This, it was just only to show that if you take the same halo, this is a set of idealized tests run with the SMUGGLE code, which is, is the attempt within a repo to simulate this multi-phase component. So this is the density profile observed for a given dwarf galaxy. And now if your modeling is something detailed and multi-phase, then you get a core at the center, accompanied by, for example, a star formation rate that is quite, let's call it bursty, but that is changing, fluctuating with time. But now in the exact same halo, you just put something of the more traditional Springel and Hernquist model that will form your stars, but will not give you a lot of outflows unless you put them by hand. So the star formation rate will look without variations, right? It's much more constant. That preserves the cusp in the inner regions. So this generated a lot of discussion in the past. I think by now there's consensus that what is going on is that as soon as you let your gas become cold and dense enough before you transform it into stars, then that will create fluctuations of density in the inner regions, fluctuation of potential that heats up your dark matter and your stars. and ends up being something as a core. It moves the dark matter from the inner regions, those fluctuations. Yep. This is an isolated one. A setup NFW that goes into a core. Yeah. So it seems like everyone agrees. However, we do require for this, which is great because then we would understand the gas core problem. However, we do need this burstiness in a star formation, or these variations that are correlated with actual movement of enough gas to heat up or to change the gravitational potential of these dwarfs. And it is kind of unclear whether the level of fluctuations in star formation that a lot of the models predict is realistic. We don't know, right? So if once we start looking at, and I will pick on fire, but other simulations too, if you look at fire simulations, they are great, but you do see a level of breathing mode that is unclear whether it is consistent with observations or not. And actually, Alison was showing me their model might not be that bursty, yet achieving cores in any case. So a lot of interesting things moving on now. And the question is, this is all nice. We model the multi-phase status of the gas. Is this realistic? And so in the process to do that, or do we need actually a different way of dark matter to create these cores? So how do we convince ourselves that CDM is still okay, provided this burstiness? And so this is something we looked at with Jan Berger using a smuggle. And the question is, what you see over here is a density profile. Again, this is an idealized run in which you put this baryonic feedback to form a core, and that would be your green line here, very nice core. Or you put now SIDM in your dark matter halo, and then you can get exactly the same density profile, right? And in order to control the burstiness, what we use is this density threshold for star formation. But that's really not the physical quantity to remember. It's just the question we are trying to see this is, okay, so if dwarf galaxies have a core, how do you distinguish whether that is because of this baryonic process or not? And what we came up with is, if burstiness forms these cores, you should have a signature in phase space of the stars. And this is kind of the proof. This is the radial velocity of your stars, and this is the distance. And both galaxies were simulated within CDM. So for now, this is not important. But in this case, your density threshold for star formation is very low, which means your star formation rate will be smooth. And this one has a very high, or it's higher density threshold for a star formation, and then it's much more fluctuating. And what you see when you catch, these are families of stars formed at the same time, very narrow H bin. You should see, for example, a smooth gradient in terms of metallicity and a much well-defined velocity space than if you have a bursty one. And the issue, well, not the issue, but the signature here is that this rapid movement of gas that happens when you have this bursty star formation imprints or alters the orbits of your stars. It changes the angular momentum and energy depending on the phase at which your star is in that orbit. And that gives you this characteristic shells in radial velocity and distance, which you can see in metallicity would be a nice thing to observe, but you can also just see it in density. That is the bottom panel over here. We have checked that the features are preserved also in projection. So we're kind of excited to bring this up to observers that can help us see whether these signatures are there. Of course, the ideal population, or the ones for which the data exist, is the dwarf spheroidals in the Milky Way, but those are quenched. So we need to catch this within, these shells will dissipate in 1 or 2 gigayears. So the dwarf spheroidals in the Milky Way are not the best. But so the idea would be to get a sample in which you can resolve this information, even if projected for individual stars in star-forming dwarfs. And if those cores were formed because of this variation in star formation, we should find the signatures in the energy space of those stars. Okay, so moving on to things that are coded here as perhaps more and more puzzling tensions with lambda CDM. I wanted to pick a little bit on the diversity of dwarf sizes. What I mean for that is, for example, if you put stellar mass versus size characterized as the radius enclosing half the mass or the light of your dwarfs, what you see is simulations are in colored symbols. Again, compilation of the best simulation state of the art that we see. And the data from the local group is in the gray squares. And overall, it looks like quite okay. I mean, this is perfect compared to where galaxy formation was when I started my PhD. Okay, so this is really amazing. However, when looked in detail, you can see that individual simulations, so if you pick the symbols of the same color, they're quite narrow. They really don't span a large degree of sizes at a given stellar mass. I mean, Applebaum is work from Allison's group. They do quite well compared to perhaps the others. They have a large sample of dwarfs. They pick some of that variation, but very compact dwarfs are a problem. And very extended dwarfs are also a problem. They are not that common in our simulations. And it seems like the local group has no issue into solving or forming things this extended. Now, if I concentrate for a bit on the high end here, things that are diffuse, because it's where my group has been working lately, we can actually expand these two systems in, not outside the local volume. For example, going to the local clusters. And what is very much connected to this population of ultra diffuse galaxies, what you see over here is a collection of galaxies from a lot of places. Again, effective radius, stellar mass. And so again, what is striking is look in this area over here, the diversity of sizes. You will have things that are as extended like the Milky Way, things that dwarf mass extended 3-4 kiloparsecs half mass radius, or things that are almost comparable to globular clusters. Okay, so that several orders of magnitudes is very difficult to get in simulations. Yeah. But well, so lately, this ultra diffuse population has caught the attention of many of us. The idea would be that these things are, dwarf mass, but sizes that are quite large. Because this is a picture from the discovery or the rediscovery paper by Van Dokkum in 2015 in COMA. Some of these first objects were found to have a lot of globular clusters. And that's very extremely interesting because the body of the galaxy is very diffuse. However, they have a lot of these dense clumps. And so exactly how those processes went about were not very clear. But one solution that was the original proposed by Van Dokkum and team was that they were actually halos that destined to form something like the Milky Way. But then, because the globular clusters formed earlier, you formed all the globular clusters they should have, and then the stars or the body of the galaxy was somehow prevented from forming those stars. And then you get most of the globular clusters, but a very truncated amount of the star formation. So that was one of the specific formation scenarios, the one that was first proposed. Later, some people started finding evidence that perhaps not all of the UDGs were so extreme, lower number of globular clusters, or even not so extended. So a bunch of models explaining ultra diffuse galaxies living in dwarf halos appeared, and actually we have not really problems in forming UDGs in dwarf halos. There are a bunch of either internal processes connected to mergers or to feedback itself that can create extended things. High spin halos was proposed using semi-analytic ideas of how the angular momentum in the gas is inherited from the halo. But then, because they were first pointed out to exist in clusters and groups, then you can also explain large sizes by either quenching and then fading away with as your surface brightness goes down, or by run pressure, or by tidal interaction, or a combination of this. So it looks like, in a way, forming diffuse objects in dwarf halos is not an issue. Milky Way-like galaxies, while the idea sounds good, no cosmological simulation has been able to form anything that looks like this, right? So we decided to look at this using the TNG50 simulation. This has the advantage of sampling very different environments. So this was the point that Jose Benavides, he started working on TNG50 1 or 2 years ago. And so we find several of these objects. And as you can see, highlighted are in red. They are satellites, and they will tend to be red and quenched as the observed ones in Coma or in Virgo. But also we find a population of these objects in the field that will be star forming and gas rich. One of the things that make it perhaps interesting, this, in my view, this job is a very well-defined criteria for what is a UDG or not, but that lately in the literature it has been a bit mixed. So what we do is we define UDGs as the outliers of the scaling relations. In this case, this is the mass size relation. And what we do is we take anything that is at a given stellar mass, the 5th% most extended. And that, if you see here in purple, are lines of constant surface density. That's one of the criteria some other people has used, or a given criteria on size. What we do is just, we select the outliers. What makes a galaxy be the most extended possible at a given stellar mass? And what we find, we did the TNG50 treatment, is that that correlates with the higher spin halo. What you see over here is a stellar mass versus the spin of the halo. And for now, look only at the blue signs. Those are our field UDGs, isolated UDGs. And so the overall population of TNG50 would have an average spin parameter about 0.035 as expected, and is shown here by the black line. You can see clearly that the median of our UDGs in the field is elevated by almost a factor of 2. So they are spins, they are halos with a larger spin. And to a certain degree, the satellites also follow the same trend. The satellites are complicated. You have to measure them at higher redshift before the infall. So the signal is a bit washed out there. But not only they have a high spin, we also find that they all live in dwarf halos. All right, so this is a stellar mass versus halo mass. But also at a given stellar mass, they tend to be a bit overmassive. And the combination of those two things, a slightly larger halo with more spin, ends up being what gives them the more extended sizes. This is kind of interesting in the sense of it's the confirmation of one of the first models by Amorisco and Loeb that was proposed based on analytic calculations. This is kind of the simulation that agrees with that model. It's not found in other simulations. Other simulations find complete independence with lambda. So the judge is out there exactly which is the mechanism that can form them. What you see over here, those square ones, we were like, okay, why do they have this crazy halo mass? And you can trace them back to be objects that have interacted with something in the past. You see, you have it over here. One of these examples is a galaxy that today is very far out in the middle of nowhere. But if you follow their history back on time, they were associated to a group, and that caused quenching. And so what we predict is also a population of UDGs in the field that should be quenched. It's an outlier population. We can make some predictions of where they should be. You see, the blue ones are field UDGs that were never processed by any other host. But objects like this one, for example, I think this one is our most extreme UDG, that is a backsplash orbit, can be today 3 to 4 megaparsecs away. So you would think it's an isolated UDG, but actually had an interaction with this object in the past. And this is important in a way, because if you just think about whether UDGs form for internal processes or external, you should always remember that some of them might look isolated, but are actually satellites in a way. In TNG50, this population of quenched isolated UDGs is about 25% in the lower mass end. So we predict that there should be, a sizable population of very low surface brightness objects in the field that are quenched and explained by backsplash orbits. And with that, I'm very much connected. I wanted to give some words on the diversity of rotation curves with a slight twist. So this problem was originally proposed as the idea that if you look at dwarfs that rotate at a similar terminal speed, right? So the rotation or the V flat is similar. The inner regions do things that are very different. So it can be cuspier than an NFW profile. So the data, these are 3 particular examples. The data is shown in symbols with error bars, and what is expected of a normal NFW with some variance is shown by the curves, color curves or black curves. And so this particular UGC 5721 would be something that rotates faster than an NFW in the low, in the small radii, something that kind of tracks an NFW, all the way to things that have like turbo core, okay? And so the issue with the problem is like, okay, we can all agree that, perhaps the burstiness of star formation can create cores, but then every halo should have a core. Or we could say, well, the burstiness is just exaggerated, but then every halo should have a cusp. But creating that some of them have a core, some of the cusp, and some things are even more cuspier than an FW, that is the problem, yeah, within lambda City. I want to pitch this as a related issue that is, okay, what happens for dwarf galaxies where you don't have gas? You cannot measure this, you don't have rotation curves. But you can measure the kinematics of the stars or of the globular clusters. And that's something that has happened for the UDG samples lately because of the great deal of attention that they have gained. So what you see over here is work done in the Virgo cluster. Of course, it's an excellent laboratory because it's relatively nearby and you can actually observe and resolve the globular clusters. There's 3 examples, 3 UDG galaxies for which we targeted globular clusters associated, or we thought they were associated to it. So you can see over here, these circle objects are globular clusters that were tagged, and the red ones are the ones confirmed to be members. So once you have that kinematic traces, you can compute a velocity dispersion from them and then come up with how much mass do they have within a given radius. Is the equivalent at one point of a rotation curve. We extended that to all the UDGs in Virgo that we could target with enough number of globular clusters, and that's work by Elisa Tolova, presented earlier this year. And what you can see is quite exciting, actually. This is velocity dispersion, one velocity projected as a function of magnitude. Our UDGs were in this area, so that's marked in gray. And what we find is a very wide range of velocity dispersions. So we have some of them that are very low, almost or lower than, for example, DF2, which is the child post for dark matter-free UDG that has attracted a lot of attention. And in our case, this UDG label 10 here, you can actually see it here, is this guy, that is this guy, VLSBD, that is very elongated. So in our case, this very low velocity dispersion corresponds to tidal stripping. Right? So we could form things like this just by tidal stripping. Might not be the case for DF2, but things this low in mass We're not too worried about them in the environment of Virgo, at least. But now the question is, what's going on with these guys? These are UDGs that are rotating too fast given their stellar mass, and is, if you want, the first kinematical confirmation of scenario like the first proposed by Van Dokkum team, saying this could be failed galaxies, galaxies that are living in a dark matter halo of 10 to the 12 solar masses, but formed only a bunch of stars and stopped. Okay, and before the hint came from counting globular clusters, this case is a bit more robust by going and actually measuring how fast they move. So we wanted to compare this with simulations, but of course we don't form globular clusters in simulation, and we wanted to make a bit more close comparison to what we were observing. So Jess Doppel worked on implementing a tagging method into cosmological simulations to mark globular clusters. And this is a snapshot of her paper. The method, I will definitely not have to go time to go in detail, but the idea is we know of a correlation between the mass in globular clusters and halo mass. We calibrate that for massive galaxies and extend that for dwarf galaxies in groups and clusters. It's the only assumption of the model, and then we pick things that are distributed like globular clusters, add info, and then we follow them through their evolution. And so the catalog gives reasonable numbers for, this is a picture on the number of globular clusters as a function of stellar mass. Remember, anything below 10 to the 9 is a prediction of the model. Above might be a bit calibrated, but the model is shown in black, observations in color, the same with specific frequency. This is for the normal population of dwarfs. So the question is, what happens with the UDGs that are formed in TNG 50 and their globular clusters? And so this is work that appeared in arXiv last week or 2 weeks ago. These are our predictions for the number of globular clusters function of stellar mass. Our simulated UDGs are in yellow, which go kind of okay with the dark purple that are observations of UDGs in groups and clusters. And the normal population of dwarfs is always shown in gray. So you can see the gray and the orange are not very different, and that's because in TNG 50, UDGs are dwarf galaxies. So that's why they correspond so nicely. And in terms of observations, it explains a lot of them, right? It's okay, and it explains a lot of the dark purple. But we seem to be missing some of the ones that have a lot of globular clusters. Those do not form naturally, at least not in our very humble formation scenario for globular clusters, okay? Now, when we measure the velocity dispersion, that we can do exactly the same that the observers do, and that's the power of this work, we find that we struggle a bit to explain this very high velocity dispersion. We have some, but they are not very abundant. And we look a bit better into selection effects or projection effects. And we find, so I will rush through this. These are 4 examples of simulated UDGs for which we tag the globular clusters and we select them in the same way than the observers. And so while for most cases, we pick up the right globular clusters, the globular clusters that are associated to the dwarfs, those are highlighted with the blue square over here. Some cases, you can have interlooper globular clusters coming into your selection box that is shown here. It happens for S6, for example, but those are globular clusters associated to a companion galaxy. So the observers look at this and it says, like, don't worry, this is not affecting us because we wouldn't choose something that looks this messy. If you have several galaxies on your line of sight, you wouldn't look at it. But this case is interesting, S8. And it shows a case in which by chance, within your selection effect, you are involving 4 intercluster globular clusters and you're labeled them as members. And the issue is because you have a typical sample of 10 or even less globular clusters, if you even put 1 or 2 interloopers, it can make your sigma really high. In this case, for example, it went from a true sigma of 33 kilometers per second to 93. All right. So in that case, you would say, oh, this is perhaps one of these failed galaxies, but it's actually just contamination. So as much as globular clusters are very useful traces because of the discreteness, we conclude that anything that has less than 10 globular clusters, it might need confirmation of this very high velocity dispersion from the stars. And we're trying to do that, but they are very faint. So you need to convince any tag to give you an enormous amount of time to just get 1 sigma. This gets even more crazy if you take into account some constraints, biased or no bias, but this is the only constraints that we have on the velocity, circular velocity of field UDGs that start forming. They can use the gas for that. And what they find is the complete opposite. So at a given stellar mass, they rotate too low. So we have UDGs that seem to rotate too fast, and we believe are failed galaxies living in very massive dark matter halos, to things that rotate very low. So that is, in a way, this diversity of rotation curves, right? Similar luminosity, completely different kinematics. And I don't have an answer for this, but I just thought it's an interesting problem to bring up. And with this, I will just leave up my conclusions and take your questions.
If you have questions, you can just unmute your microphone. And questions here over Zoom.
Thanks, Laura, for that beautiful overview. Really nice overview of the field. So a question about the size puzzle. Of course, the observed sizes are typically measured the sizes of the light, and it's also the projected light. So I'm wondering whether color gradients could contribute to some of the diversity, right? So if you had a diversity in color gradients, then you would end up with a diversity in observed sizes. So have people done the exercise of taking the simulated galaxies and actually producing light profiles and doing the projection and all of that to really test that?
I think that's a very good point. Let me actually bring back the plot. Perhaps it helps. I think some of the diversity might come from, I'm completely lost on where the plot is. Here it is. All right, some of the diversity might come from doing that exercise. It definitely adds. But what I think is missing is these extremes. These are things that there is no color gradient that will help us form an M32. These are really might be outliers or weird cases, GR8, or these are very compact, high density dwarfs that I believe are not there in at least the simulations we looked at. So Alison just showed me some new ones that might be perhaps a bit more promising, but from the ones that I have looked at or come close to, projection effects really isn't the problem. The problem is this burstiness. It will tend to always, it's the same process that forms the dark matter core. It just heats up the stars and you have a bubble now. So yeah, the very compact ones, I think is a very interesting one. Thanks.
More questions, Adrian?
Thanks for the really nice talk. So if you go all the way back to when you're showing the comparison of the phase space for 2 dwarfs, one that had a bursty star formation history, one that was more stable, and the metallicity gradients.
Yep.
So you were, and this is a straightforward question, but you were saying that you wouldn't be able to see the types of shell features in the Milky Way dwarf spheroidals just because it would get washed out. But is that true? Like, wouldn't these 2 profiles lead to differences in the correlation between the density profiles and the metallicity profiles, even after they phase mix these shell structures?
But it's true. What you're saying is, forget the shells, just look at the gradient.
And compare that to the density gradient, the gradient in the phase space density.
Yeah, okay, good.
Maybe in the comparison of those 2 things.
Yeah. It's an interesting point. I think the issue, and it might be related to the chat we had before, is that we don't really know how it should look like. This is a model for which there was some enrichment in, but I wouldn't trust that too much. Right. All right. So if we measure only the gradient, I wouldn't know if it's because the simulation has the wrong gradient to begin with, or because it's the phase space density the one that is causing the difference.
Fair.
So I think it's more robust to think about, as to just think about phase space density, because the shells, you know, it's independent of how you're. We showed it here in metallicity just to add another dimension, but in density they show up maybe equally well, and that would be a nice confirmation to have. That's a good one.
Alison, yeah.
I had a question. Back near the beginning when you were showing the LMCs, how like galactic is little.
Oh yeah.
I just thought they were really interesting because you know your cutoff prediction has some high mass companions around LMCs, but your galactic results don't have very much.
Yeah, I don't know. We haven't looked at them in detail, so we just provided for different masses ranges what were the predictions. So yeah, well, we have to look at the high mass. They are not. Yeah, they are not selected to have an SMC. So this is bias, and I guess what is going on is the typical stellar mass function is a bit. It doesn't favor to have an SMC. However, you know, the predictions from Santa Santa's was also taking a general population of LMCs. So yeah, I don't know, haven't thought about it, but thanks for pointing that out. Yeah.
Shai, yeah.
So you said in TNG50, UDGs tend to have higher spin and low or high halo mass per stellar mass, but are those things enough to explain them? Or if, in other words, if you make selection on those two criteria, do you get UDGs, or are UDGs
not exactly. Those are general trends. You can see over here, and I don't know if I put the right plot. I'll try to check if I did. So you can see that there are a lot of gray points that are overlapped with our blue stars. So those have a high spin, but they didn't end up as a UDG. Then you have, you know, the selection here, but again, there is a lot of overlap with the grays. So what we thought it was more robust is, oh, I didn't put it, no. All right, so what we found that the UDGs maximize, and let me just sorry, I don't have the right plot, is, think about MoMA and White model, all right? So you bring a given fraction of the mass, and that captures a given fraction of the angular momentum of the halo. So the UDGs maximize that. At a given MD, also, where MD would be the mass of the disk or divided the mass of the halo, at a given MD are the ones that capture most of the angular momentum of the halo, okay? And those really looks like those are a bit more extreme in that space. Now, exactly why did they achieve that will have to do with the timing at which they started cooling versus the timing at which they had the mergers, etc. But what we found is those are maximums the angular momentum compared to how many baryons they managed to put in the inner regions. Yeah, sorry for not having the right plot, but it's there in the paper.
Yeah, maybe back to the cusp core problem. You had this slide where you said that.
I didn't know Jan was here. Of course, he is the author of the paper. How crazy!
Also comment on the question before later, but
I hope it's not about your paper.
No, my question was gonna be a bit about something else.
Okay.
Which is where you said with the model like Smuggle, where you resolve the multi-phase ISM, you would always get the course, yeah, this exactly. But doesn't this also depend on, especially in isolated runs, the initial conditions that you choose to some extent, the gas fraction, for example?
Right. So I simplified here a little bit the parameterization of this. So really, the burstiness is not really what matters, but what I think Jan is getting to is that what you need is that the gas is locally dominant in your potential. It just happens to correlate when that happens, that you get these variations in star formation rates. And that's why I was kind of framing it like this. But I think the physical quantity to take into account is that you have to have locally spots of dense gas that dominate the potential. So in a way, it will depend on the gas distribution. As far as you achieve that, then if you have a disk that is very, 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 very extended and the gas never really dominates locally, perhaps you would not really form a core. Jan, is that the question?
Yeah, I was getting more to, since this is an isolated setup, in zooms or cosmological runs, like with fire, for instance, you would get core formation essentially all the time, right? Do you think that this would also, does this also happen in SMUGGLE or in other models like that? Or could there be some variety where some dwarfs actually don't form a core despite the more bursty feedback?
Okay, good. Thanks for the clarification. Yeah, so I know people working on fire has looked at this, and what they see is that if your galaxy stops forming stars, then the cusp kind of regrows. All right, so you need the constant injection of energy in order to preserve the core that you formed. And in that way, there would be a prediction that, your more star-forming dwarfs should be core, whereas the other ones should be a bit more cuspy. That I don't know if has been followed up with observations, but then I think also Alison showed me some excellent or new simulations that I don't know yet, but she also manages to form quite a variety of velocities. And so not always it will form a core, but we have to wait for the big